Hello everyone. So today I will talk about glassiness on a different type of system. The title of my talk is Glassy Dynamics in Confluent Biological Tissue, and this particular work is done in collaboration with Saroj Kumar Nandi from Tata Institute of Fundamental Research, Hyderabad, India. So Glassy Dynamics in Confluent Monolayer, where the packing fraction is always equal to unity, is crucial in biological processes like wound healing, bronchial asthma, morphogenesis, etc. And it is different from particular system. The system is important in glassy perspective as it shows unusual glassy behavior, and glassy aspects still remain unexplored in this type of system, and so therefore developing a detailed theoretical framework for the glassy dynamics of such system is an important task. So one ideal paper which characterizes glassiness on this type of system is basically the paper by Angelini, where they showed the heterogeneous length scale and mean migration feeds with respect to the cell density shows this glass-like behavior. And the paper by Park, they also showed that this mean square displacement and the self overlap function and the 4-point correlation function also showed glass-like signature. And now, this type of more simplified version of this type of confluent system can be modeled via this vertex model and the Voronoi model, which are basically the continuum model. And the discrete version of that is basically the cellular Potts model. So there are many studies on this vertex and Voronoi model, but there are only few studies which have done on the cellular Potts model. So in vertex model, cells are basically represented by this polygon, which will till the space. And in Voronoi model, we basically took the cell center of mass and took the Voronoi tessellation out of that to form the cell. And now in cellular Potts model, we took the square lattice of size L cross L to represent the confluent monolayer, and each cell in this lattice is represented by a set of same integer Potts variable sigma, where sigma runs from 1 to total number of cells. And here the cells in this model evolved by stochastically updating one lattice size at a time, as you can see here, through the Monte Carlo simulation via an effective energy functional age with an area and perimeter constant. And A naught is basically the target area, and P naught is basically the target perimeter. So now, due to geometric reason, in this type of model, basically the concept of confluency and the underlying lattice for a given area of a cell, there is a minimum perimeter, and which basically characterize two distinct regimes of P naught in this type of system, which is basically low P naught and large P naught regime. And in low P naught regime, most of the cell will not able to satisfy the perimeter constant, for which there will be a strong repulsive interaction term which will arise in the Hamiltonian. And for large P naught, most of the cell will able to satisfy the perimeter constant, which ensure the perimeter constant to be equal to 0. So in our case, or in our simulation, we took the initial cell size to be 5 cross 8, and which ensure the p minimum to be equal to 26. Now let's have a look on the dynamics of this in this type of system. So here you can see this at low P naught regime, the cells are basically soft and compact object, and the cell center of mass trajectory shows caging like behavior at low temperature, and cells are moving randomly in large temperature. So, and the mean square displacement and the self overlap function also shows this glass like signature, as you can see here. So now at large P naught regime, the dynamics is not very much different from the low P naught regime. Only difference is that here the cells are basically irregular shaped objects. So now, to keep the system in a glassy state, we must avoid crystallization. And a monodisperse system in 2D easily crystallizes for point particles, usual point particle system. And this model is different from the usual point particle system in the sense that it has a clear distribution of area and perimeter, as we can see here, and which basically effectively makes this system polydisperse, and also it helps to avoid crystallization in this type of system. And now this glassiness in this type of model comes from disorder energy landscape, and within this theory, the nature of the disorder energy landscape and the configurational entropy is important. And in this system, the direct calculation of configurational entropy is very difficult, and so we looked at the disorder energy landscape through a defined quantity called inherent structure energy, and the effect of geometry constant is whose result is basically these two distinct regimes of P naught, that is the large P naught and low P naught regime, and is also evident from this inherent structure energy calculation, as you can see here. Now, through simulation of vertex-based model, the quantity Q, which is defined as the expectation value of Pi by square root of Ai, has been interpreted as the structural order parameter of glass transition. And however, within CPM, such an interpretation is not generic, and the result is basically simply the consequence of geometric restriction. So here we have plotted this Q versus this P naught, and where the Q tends to a constant value in low P naught regime, and it increases linearly at large P naught regime. And the geometric restriction point is more clearer from the plot of expectation of Pi minus P naught versus P naught, where you can see that at low P naught regime it decreases linearly, and at large P naught regime it basically is equal to 0. So now, to have an analytical understanding of this simulation result, we extend the random faster transition theory of equilibrium class for point particle system to the confluent monolayer in our case in cellular Potts model. So RFOT relies on the existence of the mosaic-like picture, as you can see here in this shaded region. So these mosaics are of different states, and within RFOT theory, relaxation dynamics of the system comes from this individual mosaics. And taking that as an input, one can obtain the length scale as well as the time scale within this theory. So the expression of relaxation time is different in two different regimes. So at low P naught regime, we have this perimeter constant is not satisfied. So that's why we have a dependency on P naught on this relaxation time. And but at last P naught regime, the perimeter constant is satisfied by the cell. So that's why this P naught dependency is not there in this relaxation time formula. So for the comparison of the simulation data with these RFOT parameters, we just feed this only one set of simulation data with these four constant K1, K2, Tk, and var kappa C. So and once we got the values of this parameter, we don't have any other fitting parameter in our calculation. So for the rest of the data, we just plot this formula with this value of the constant from the first fit, and basically we plot that formula with different values of P naught, and also we plot this simulation data. So here in the plots, the symbols are basically the simulation data, and lines are basically the RFOT theory formula for low P naught regime and large P naught regime, as well as other formulas. So here, as you can see, this match is remarkably well. This match with the simulation data and this RFOT formula is quite well. And as in one of the remarkable properties of this type of system is that basically in the low P naught regime we got this unusual subarrhenius relaxation, where in the point particle system we usually got this superarrhenius relaxation, where the curve will fall on the other side of the graph. So now next is basically so we are getting a subarrhenius regime when this var kappa C P naught is greater than Tk from this RFOT formula. So from this formula one can predict that when this var kappa C P naught is less than Tk, we should get a superarrhenius behavior, and indeed we got that. As you can see in this case, when we take this P naught value to be less than equal to 23, which satisfies the condition var kappa C P naught is less than Tk. So for that case, when that values of P naught we simulate, we got this superarrhenius relaxation from the theory prediction of the theory, and also as well as from our simulation, so which also match quite well. And we also calculate this glass transition temperature from this RFOT formula, and also from our simulation data, so that also match quite well. So now we in the last P naught regime, so there is no dependency on P naught is here. So here we have the only P naught dependence can come only through this value of the tau naught. So as you can see, this log tau naught has a clear dependence on P naught, and so as this tau naught has only the dependency on P naught, so if we plot this log of tau over tau naught with respect to this temperature, so as there is no dependence on P naught here in the right hand side, so we should get a master curve for all values of P naught. So as you can see, we are getting indeed we got that, and that also match quite well with the RFOT formula. So although this is a very basic model of actual cells in a monolayer, so it matches quite well with the experimental data. So in this plot, we got this plot from this paper by Lin from Advanced Biophysics. So they have plotted the standard deviation versus mean migration speed, and they got a linear relationship with that for that. And as the system become more jammed, it basically moves towards the origin. So here as well in our simulation, we also got this exactly same type of linear behavior, and when we plot the standard deviation versus the mean speed, so and as the system become more glassy, the points move towards the origin. We have also calculated 2 and 4 point correlation function, as you can see given in this formula. So as you can see, these also match remarkably well with the experimental result from the paper by Atia from Nature Physics. And so here for the plotting, we basically rescaled our time scale, and we are allowed to do that because we are doing a Monte Carlo simulation, so where there is no inherent time scale. So that's why we scale the time in our simulation, and also we choose the simulation parameter in such a way that this curve will overlap with each other. So that's how we match this experimental data and our simulation data. So as you can see, this match is also quite well. So now, as a concluding remarks, I would like to say that we have simulated the cellular Potts model for a confluent tissue and developed random faster transition theory for such a confluent system. And the dynamics is controlled by the perimeter constant P naught that parameterizes the interaction potential. And this glassiness in this type of confluent system is solely controlled by this disordered energy landscape. And there is a very crucial role of geometric constant in this type of model. And our work, you can find our work on this archive link. And I would like to thank Professor Muskan Sri Barma and Professor Chandan Dasgupta for many useful comments and enlightening discussions. Thank you.